Einstein's equivalence principle really brought together the idea that the gravitational forces of mass can have an impact on the space around them. Much more than just the idea of a gravitational field, these objects of mass were now warping what becomes known as space-time. And that is what's well shown in this diagram here. We see the mass of the Earth, and we see how the gravitational attraction due to this large mass warps the space-time all around it. So let me go through this idea of what space-time really is. Minkowski is the mathematician who came up with this idea of space-time. So we've seen that time intervals and lengths and simultaneity is relatively dependent on the relative velocity of the observer. So we've got a lot of things here which are all dependent on the observer, and that becomes really, really complicated because it means one person sees one thing or one person sees another thing. But if we accept that velocity connects time and space, it means we need to stop thinking about space and time separately, and rather we talk about a combined space-time. And that combined space-time brings together these dimensions, and it provides a consistency if thought about carefully. So space-time is four-dimensional, so we have three spatial dimensions and one time dimension. But here the key thing here is that we've got to recognize that space and time becomes the same thing. Is it really? So let me take you through the argument. If I map something over on two dimensions, and what I'm going to map here is one is a spatial dimension, but now I've also got although still a spatial dimension, I'm using the speed of light and time to identify a location. So therefore x equals c times t, so therefore you can see that I have a straight line clearly showing this relationship. That means if I have a object traveling through my flat plane, then what is going to happen if it's moving slowly? It's going to be traveling at with a gradient which is less than that of the speed of light. Okay. As I travel faster, I have a faster moving object, then its progress through space-time is going to be closer to that of the speed of light. I cannot have anything which is traveling that's faster than the speed of light. So therefore that's an absolute rule, and there's a complete no-no there. Now we think about how we consider this motion through space. If I just had a straightforward geometrical interval, so I'm looking at an x-axis and a y-axis, and to go from one point, x1, y1, to another point, x2, y2, means that if I think about it, there's going to be a change in y and a change in x. The distance traveled between these two locations using Pythagoras' law is my change in s, which is my change in location, squared is equal to my change in y squared plus my change in x squared. So this is a standard bit of geometrical thinking along some very standard physics rulings. Now we're going to see how this works when we're considering space-time. So what we have now is that if I look at the motion from one place to another, x1 t1 to x2 t2, that means that my motion is going to be equal to c times the speed of light times the change in time squared minus the spatial change x squared. And notice how this minus becomes quite important in this situation. The reason for that is the minus sign indicates the difference between space and time. Okay, and it's kind of crucial here. So what we need to show here is that the change in displacement squared doesn't change under any Lorentz transformation. Okay, so space and time could both be altered, but the total combination of their altering means that we still have an absolute change in space-time, which is really, really important. It means that I'm no longer dependent on seeing if there's any time dilation. I'm no longer dependent on any length contraction. These two features kind of cancel each other up, so I get a value which is much more important, which is displacement through space-time. So for a particle moving at the speed of light, then what I've got to recognize there is that my change in x is equal to c times speed of light times the time, and therefore the displacement through space-time is always 0. So just like as we discussed with light beforehand, light doesn't perceive any distance. If you're traveling at the speed of light, there's no perceived distance because we have the absolute length contraction, so the distance is equal to 0. These character of space-time intervals, so if we think about it a little more closely, let's say that my value is greater than spatial distances can be traveled by the speed of light. This is true. Now, there's an existence in an internal inertial frame in which two events happen at the same position. Okay. So if they're happening at the same position, but they never happen simultaneously, that becomes a time-like distance. Okay. So what we're saying here is that the time-like distance is greater than the spatial distance. So that means there is a distance traveled, so change in s squared is going to be greater than 0, but this is a time-like distance and not a spatial distance. If we have, and this is where that negative sign came in really, really importantly, if my change in space-time is below 0, so that means it's negative. Okay. So that means that my change in distance, spatial distance, is greater than my time-like distance. So spatial distance cannot be traveled by the speed of light. There exists an inertial frame in which the two events happen simultaneously. So two events did happen simultaneously, so there's no time difference here. Now that means they never happen at the same place, but they can happen at the same time. So that means the distinction is a space-like distance. Okay, breathe deeply. I know this is kind of crazy and out there, but with practice you'll get to grips with this. Those are the general rules. Okay. Now, what we're more likely to see is considering diagrams showing this taking place. Okay. And what we have here is we have no longer, if we have a straight line on a flat plane, if we have a massive object which causes a warping of space-time, get back there, then what happens is that that my straight line becomes bent in this new situation. So let me take you through how this bending of space-time can have an impact on objects. So first of all, I'm saying is that in a flat two-dimensional space, the link between one place to another is a straight line. In curved two-dimensional space, what we have is the straight line from one place to another is curved. So the shortest distance from one point to another reflects a curved line. And these curved lines are defined by the amount of gravity, or the size of mass which is warping space-time. And the impact on the object. So what we can have here, and this is kind of interesting, is if we imagined what we perceive to be a straight line between a bowler and a pitcher. Now what happens here is, what's really happening is, if we think of light travelling on this straight line, well, this light is actually curving because of the curvature of space and the impact of the gravitational field on light. At the same time, our ball, which is travelling a straight line from the pitcher to the batsman, is also travelling in a straight line on the shortest path between these 2 points. Both of them are following the shortest path, but the influence of gravity is different for each one. So therefore, we've got 3 situations where each one, the geodesic is the straight line, but all of these particles follow geodesics, which is straight lines in curved space. Okay, that's the word for them. They follow different straight lines in curved space, which I know is a contradiction in terms, but it's kind of the terminology I'm going to try and use. So some implications of general relativity here. Okay, so first of all, a gravitational field can be transformed away at any point if we choose an appropriate accelerated frame of reference, a freely falling frame. Okay, so that means that a gravitational field, we can imagine it to be a accelerating frame, and therefore the gravitational field becomes irrelevant. The equivalence principle means that the world will just act as if it was accelerating, and that's where we see the curvature of light and the relative curvature of a ball being thrown from one place to another, although I'm going a straight line because the object where the frame of reference is accelerating. Einstein specified a certain quantity, the curvature of time-space, that describes the gravitational effect at every point. Okay. So he describes the curvature of time-space dependent on that gravitational effect. There's quite a lot of crazy things going on here. So take your time, take a deep breath, look back through this video, and then we're trying to apply this during lesson time to help you fully understand what's really going on.